Hello and welcome back, everyone. Moving on to section 5.4. It's called Coordinate Transformations for Higher Dimensional Integration. More or less, this section is set up to handle these things called coordinate transformations. You've probably already experienced some in Calculus 2, for the sake of making integration easier. So I'll just say it turns out that some quote-unquote tricky integrals a lot easier under a coordinate transformation. What do I mean by that is, let's just take a really quick example of integrating maybe the semicircle. Right, the semicircle, classic Calc 1 integral, maybe Calc 2 when you learn trig sub. You go from -1 to 1 in the x direction, dx, 1 to 1, and the function ends up being 1 minus x squared with a square root. Traditionally, you do a trig sub on this. You'd let x equal the sine of theta, so that dx is cosine of theta d theta, and then this integral would reduce to, well, root 1 minus sine squared theta cosine theta d theta, and you'd be integrating from -pi/2 up to pi/2, and you'd go through that integral from this point onwards. You use Pythagorean identity to simplify that to cosine squared, take a square root, so now you have cosine, you're integrating cosine squared, and you would get as an answer pi/2, which of course corresponds to 1/2 of the circle of radius 1. Not too hard of an integral to do, but we did have to go through that extra bit of trig sub, which is not exciting. It turns out in polar coordinates, if you recall, polar coordinates from Calc 2, depending on if you actually studied polar coordinates in Calc 2, this integral, the integral -1 to 1 of root 1 minus x squared dx, can be rewritten in polar coordinates as the integral from 0 to pi, those are the bounds on theta, and then we have r of theta squared over 2 d theta, but in this case the radius of that circle is fixed at 1, so this just becomes 1/2 d theta from 0 to pi, which of course is going to give you pi/2. You can avoid all of those trig subs. We're going to see polar coordinates look a little bit different in higher dimensional integration because of course this was our Calculus 2, where everything was a one-dimensional integral. Turns out multivariable calculus will have a two-dimensional version of the polar coordinate transformation, but you can already see how much easier it can make your life when you're integrating. And most of the time that's to avoid a trig sub, but there are going to be other things that this makes your life easier for. So I want to comment really quick, why was trig sub already showing up so often? It really results from the fact that we use the magnitude of vectors somewhat ubiquitously in higher dimensions, because magnitudes represent such important concepts. They always represent a distance of a vector, and every time you compute the magnitude of a vector, you end up with a square root of each entry of that vector squared, which is of course ripe for some version of trig sub if you're integrating. All right, trig sub is more or less developed to handle the square root of a quadratic, and so every time we take a magnitude, we're probably going to encounter a trig sub. This happens half the time in domains as well, because the balls, right, the balls of some radius r are just defined as a magnitude less than a specific radius. So sometimes the domain will have a lot of square roots of squared variables, and other times the actual integrand itself will have these square roots of squared variables. Either way, things look kind of ugly if they're left in what we call Cartesian coordinates, these regular coordinates that we've been using the whole semester. Instead, it would be useful if we could develop a system in which, notice how I use the r there, r for the radius. Wouldn't it be great if we developed a system where domains depend directly on this r rather than the variables x1, x2, etc. Right? That variable r plays a very specific role in all these domains. It kind of serves as the upper bound for everything. And so if we're just integrating the variable r, as we kind of saw with polar coordinates, the variable r was fixed in that semicircle. It's just equal to 1 everywhere. And so you get a lot easier time. You're integrating against a constant, more or less, when you have balls of specific radii, if you can actually perform some coordinate transformation and just represent everything in terms of that r. So let's talk about how to develop a theory of coordinate transformations, because we're actually going to have to go quite deep into the theory before we can discover kind of the consequences of the theory, which are a lot easier than the theory itself. The consequences will be polar coordinates for one, and spherical, which is the higher dimensional polar coordinates, and cylindrical coordinates, which are also a version of polar coordinates extended into 3 dimensions. We're going to develop the theory of coordinate transformations first, and that's how we're going to finish this video. And then in the next video, we'll actually tackle spherical and cylindrical coordinates. So the theory, very exciting, very cool, maybe a little bit intense when you start to read everything out. So what's the theory going to look like? Well, we're going to start with what a coordinate transformation actually is. And a coordinate transformation is actually a function. Okay, so this is a function. I use the Greek phi here. So I use the Greek phi for this function. That's a coordinate transformation. I would say that's a fairly common notation. And this function is going to map Rn, so some n-dimensional space, into what I'm calling x. But in reality, x is a subset of Rn. So some subset of Rn is its output. We're not going to lose or gain any dimensions in phi, because phi is going to be required to be invertible. And for phi to be invertible, there's no way you could lose or gain any dimensions. You need to map one-dimensional space to another dimensional space of equal dimension. So it could map to a subset, but it's not going to map to any lower or higher dimension space. And this function is going to be invertible. It's also going to be continuously differentiable everywhere. If you eventually take a course in differential geometry, these functions are called diffeomorphisms. That's just a fun word for you to throw around if you want to. And really, in differential geometry, even with coordinate transformations, you technically only require that you have a collection of locally invertible diffeomorphisms. We're not going to worry about that sort of idea today because it gets a little complicated to keep track of all of them being locally invertible. But for now, we're just going to say we have this kind of global diffeomorphism, and it's going to, because it's a diffeomorphism, be invertible. It's going to be continuously differentiable everywhere. And so how do we use this function to kind of induce what we call new coordinates? Well, we induce new coordinates with this function. We call them the phi coordinates. So the phi coordinates are just induced as the image. They're the image of the variable x under phi. And I'm going to call them x tilde phi as my new coordinates. And we just take any original variable, x, and map it under phi. And of course, since phi is invertible, you can go back and forth between the two coordinate systems. And so we just call the output of phi our new coordinate x tilde. And of course, since its output is a subset of n-dimensional space, there's going to actually be n distinct entries in my new coordinate, my tilde coordinate. So there'll be n distinct entries in there, and they're all, of course, just the distinct entries of the output of phi. We just call those the new coordinates. Of course, because we're thinking about coordinates representing n-dimensional space, we have to associate, even though phi is a multidimensional function, you can think about phi as actually exchanging the locations of points. That's not what we want to do. What we want to do is think about phi as not exchanging locations of points. In other words, this, when I say geometrically equivalent, what I'm saying is that we interpret, that's the important thing here, math is all up to interpretation. So we interpret the outputs of phi, which recall are the new coordinates, as different numbers that represent the exact same points. Let's say exact same points in space. That's what's kind of funky about coordinate transformations. You're applying this function, and you're clearly getting, because you're applying a function, a new collection of numbers out of it, but you say, hey, I'm not reinterpreting that new collection of numbers as a point in some other space. I'm actually going to force the input point and the output point to be the same geometric location of a point, and I'm just allowing myself to have new numbers that represent that geometric location. So that's how we interpret those. And then finally, here's that idea of Cartesian coordinates that hopefully you experienced in Calculus 2. The Cartesian coordinates are, of course, when phi is just equal to the identity function, or in other words, it's the set of coordinates that we always assume we're starting with. It's kind of the set of coordinates that the vector space of Rn is based off of. And so the regular coordinates we've been using our entire lives are called Cartesian coordinates, named after Descartes, who has this apocryphal story about a fly zooming around his room. And I think he was stuck inside, maybe he was sick or something. And he realized that it took exactly 3 different numbers to identify the location of the fly. It was a forward-backward number, a left-right number, and an up-down number. It could uniquely identify the location of the fly in his room because of this apocryphal story from Descartes. There's your Descartes in our Cartesian coordinate system. But we will have all sorts of other coordinate systems, and I'm just going to bring up kind of the one you probably have experienced before, which is the polar coordinates. So at least in R2, we can see an example of a coordinate system as the alternative coordinate system as the polar coordinates. And so let's recall what these polar coordinates look like. Well, they have this coordinate transformation function, right? We're still going to call it phi. This is going to map R2 to, notice this is my subset of R2 on the output. So this is that special subset of R2 in the output. Notice I don't have a complete R2 in the output, but it's still two different variables that are determining my unique points. And what does phi look like as a function? Well, phi's first output is the square root of x squared plus y squared, right? If I take two variables in, my R2 variables, into my function, then the first output is just the square root of those variables squared, added together. And then my second output is this thing called a tan 2, which I will describe later. You can think about this as tan inverse in quotations. It's tan inverse, but associated to the correct quadrants. Right, technically tan inverse only has the ability to output values in the first or fourth quadrant, and you would want to have the ability to get some values in the second or third quadrant as well. So a tan 2 takes care of that for us. Okay, and I've actually got the definition of a tan 2 down here. What you can see happens is we really do pick up the regular inverse tangent. When x is positive, what do I mean by that? It's the same as what I was just describing. Inverse tangent is going to give me everything correct. Let's put a unit circle on here. So you can give me everything correct on the first and fourth quadrants, because inverse tangent can give me any of those angle measurements. Everything else that's thrown in here, so I'm going to add pi to my angle measurements when x is less than 0 and y is greater than or equal to 0, so that adding pi is going to take care of this portion for me. And then I'm going to subtract pi when x is less than 0 and y is less than 0, and that subtracting pi is going to take care of that portion for me. And then what I actually have is this pi over 2 when x is equal to 0 and y is positive. That's just this very top point. And then I've got negative pi over 2 when x is 0 and y is negative, and that's of course this very bottom point here. So that's how a tan 2 actually works. And just to give you an example of a few evaluations of a tan 2, let's say that I want to evaluate a tan 2 of 1 comma negative 1. That means I'm going to take the y value 1 and the x value negative 1. If I plot that on my unit circle plot up above, I've got a y value of 1, which is up top, and x of negative 1. We're over here. This is the point, negative 1, 1. What is this angle measurement? Well, of course, I think everybody can tell the angle measurement there is 3 pi over 4. So this would just be 3 pi over 4. You just put the x and the y values on the plot and see what that angle measurement from the positive x-axis happens to be. That's what a tan 2 does for you. Really is just a fancy version of inverse tangent. So you've seen this before with polar coordinates. Often we're going to define the first output of the polar coordinates, which is this square root x squared plus y squared term. We define that to be r. And we define the second output of this polar coordinate transform, which of course is a tan 2 y comma x. We call that theta. We have special names for these. R is called the radius. And maybe you didn't use this next special name, but it's so much fun to say that we're going to use it. Theta is called the azimuth, or the polar angle. But I like azimuth better. So we'll call theta the azimuth and r the radius. And so the whole point of coordinate transformations is that we associate both of these, right? We associate different notations to the same geometric location. Different notations, but the same geometric location. And we'll see that in our first example below. We can also talk about the inverse function, right? Because every single coordinate transformation needs to have an inverse. It needs to actually be a differentiable inverse, right? And so our inverse function, what does the inverse function look like? Well, of course, it's going to map the space that we ended in, this r theta space, into R2. So it's going to map from where we ended up into R2. And what does it look like? Well, we know this from working with polar coordinates. The x-coordinate is just equal to r cosine theta, right? X-coordinate is r cosine theta, and the y-coordinate is r sine theta. And so this is how we translate between, right, back and forth between polar and Cartesian coordinates. Is if we want to go into polar, we take square root x squared plus y squared for r, and we take a tan 2 of y comma x for theta, and vice versa. If we're already presented with r and theta, we take r cosine theta, and we call that x, and we take r sine theta, and we call that y. So everything should feel somewhat familiar if you actually covered polar coordinates in Calculus 2. Now let's look at an example of the polar coordinate transformation in action. So we have is a couple points here, a couple Cartesian points, right? So we've got 1 over root 2, 1 over root 2 as a Cartesian point. We have negative 2 pi comma 0 as a Cartesian point. We have 0 comma negative root 3 as a Cartesian point. And if I plot those three Cartesian points, as I've plotted here, you can see what's going on for each of them. So how do we interpret a Cartesian point? Well, that x-coordinate just pushes me out along the x direction, and then the y-coordinate pushes me along the y direction, and then our terminus is where we call the point. So there's 1 over root 2, 1 over root 2. We also have something like negative 2 pi comma 0. The x-coordinate goes out negative 2 pi units in the x direction, and then we don't move at all in the y direction, so our terminus is the point. And then the point 0, negative root 3, we don't go anywhere in the x direction, but we go negative root 3 units in the y direction, and then the terminus is our point. So those are the 3 points in Cartesian coordinates and how you might think about them in space. But then you can apply the polar coordinate transformation to these, right? And if you remember what that polar coordinate transformation looked like, you take the x input and the y input, and you take the square root of those inputs squared for the first output. And of course, that's going to be the square root of 1/2 plus 1/2 for my 1/√2 point. Square root of 1 is 1. So that's going to give me my first output of my polar transformation. And then I'm going to take a tan 2 of the x coordinate, 1/√2, the y coordinate, 1/√2, and of course, a tan 2 of the point 1/√2, 1/√2, which is on the unit circle, is just pi/4. So that's going to be my second output. And recall, we think about this output as the radius and this output as the azimuth. Okay, we can also apply our coordinate transformation to negative 2 pi and 0. We're going to take the square root of negative 2 pi squared plus 0 squared, which is just going to give me a positive 2 pi. And we take a tan 2 of y comma x, which because we have 0 for y and a negative x value, that's going to give me pi here, because that's going to be on the left side of the unit circle. So that's going to give me pi. We can also take the polar coordinate transformation of 0 comma negative root 3. Square root of 0 squared plus negative root 3 squared is just going to give me root 3. And then a tan 2 of the y component, negative root 3, comma the x component, 0. A tan 2, that's straight down on the unit circle. And straight down on the unit circle is an angle of, well, I wrote it as 3 pi over 2. Technically, a tan 2, as I defined it, would also give me negative pi over 2. Either one's fine, right? These angle measurements are totally acceptable up to multiples of 2 pi. So if we then plot these outputs, right, we can plot them and we interpret something like 1 comma pi over 4, the radius, as moving along the positive x-axis first, and then pi over 4 is an angle that pushes me away from the positive x-axis. But you'll notice that this point, the point is geometrically equivalent to the Cartesian point 1/√2, 1/√2. Like in some sense, they haven't moved, even though we're representing them differently. And we can look the same for 2 pi comma pi. That means we go out the positive x-axis by 2 pi units, and then we take an angle measurement of pi around the axes, and that's going to end me up where I ended up before. And again, we are geometrically equivalent to the point negative 2 pi comma 0. And if we look at root 3 comma 3 pi over 2, we go out root 3 in the radial direction, and then we go around 3 pi over 2 as an angle measurement. And of course, you could also do this negative pi over 2 angle measurement would also work. You still end up at the same point. And when we use that, root 3, 3 pi over 2 as our polar coordinate, you can see actually this point is geometrically equivalent to our original point 0 comma negative root 3, the Cartesian point of that. So that's just one case of thinking about a polar coordinate transformation. It's kind of our favorite coordinate transformation. But I also want to bring up that you've actually been using other coordinate transformations your entire calculus career, because u substitutions are actually always coordinate transformations. So every time you've used a u sub in calculus 1 and 2, you've been performing a coordinate transformation. Let's look at an example here, and I've given myself the calculus 3 notation for an integral, even though it's going to end up being a one-dimensional integral. So let's think about this integral over omega of the function f with respect to the volume form. But I'm defining my function f as a one-dimensional function, so the volume form is just going to be dx. We're going to take this function, which is x plus 1 divided by root x squared plus 2x plus 2. We're going to integrate over the domain. X is between 0 and 1. So of course, in calc 1 terms, it looked like this notation, the integral from 0 to 1 of the function x plus 1 over root x squared plus 2x plus 2 dx. And in its current form, it's very difficult to integrate. And what I'm trying to emphasize for today is that by performing coordinate transformations, we make integration easier. And you used to always call this u sub. We're still going to use u sub, but we should start to interpret u sub as a coordinate transformation. So what do we actually do when we do u sub here? This is a classic problem where you take u to be what's inside of the square root, so that's going to be x squared plus 2x plus 2 here, and you compute its differential, which is of course the derivative of x squared plus 2x plus 2, and then dx, so we get 2x plus 2 dx, or we can factor out a 2, and we see x plus 1 dx, where importantly that x plus 1, which is a portion of my du, has already shown up in the problem. So in other words, the x plus 1 dx that's in the integral can be replaced with 1/2 du. That's nothing new. That is the u sub all of you know and love. And so I replace everything in the square root with my variable u, and I replace x plus 1 with this 1/2 du. And then all of a sudden we can integrate my new integrand, which is really u to the negative 1/2 power using the power rule. And we're just going to add 1 to the power to get 1/2 divided by the new power. And then this is what's really important. We evaluate, right? If you don't send yourself back to the x coordinate system, we evaluate on new bounds. And what I'm claiming is that these new bounds are actually a coordinate transformation of the original bounds, right? The act of starting out with x min at 0 and x min at 1 you go up to u min is 2 and u max is 5 because you just evaluate the function u on x min at 0. Imagine if I put 0 in, 0 in, 0 in, I'm going to get a 2 out of that. And you also evaluate u at x max, which is a 1. Imagine if I put a 1 in, a 1 in, I would get a 5. And so you're evaluating those original bounds inside the function u. It doesn't look like u is a function of x, but really u is a function of x here, and you're evaluating the original bounds 0 and 1 inside of that function of x to find the new bounds 2 and 5. And if we think about the coordinate transformations, what do we actually do with a coordinate transformation to find out where the output points are? You evaluate the original points on the inside of the coordinate transformation to get these output points. That is what the function u is actually doing in a u sub. It is translating the points over from one coordinate system to another. And more importantly, we are able to claim that the output of this integral, the output of the integration with the u sub, has the same area, right? The only reason we can claim that the area in the variable u is the same as the area in the variable x is because we associate them to be geometric equivalent. Right, geometrically equivalent. We're not actually changing the shape of the geometry of this area under the curve by performing a u substitution. And it's very interesting to think about it that way, right? That every time we've done a u substitution, we're really, because we're changing the bounds, so you would expect that the shape and the area of this function changes, but it doesn't, so long as we actually agree with this geometric equivalence idea. And the way that we're actually accounting for that little bit of geometric equivalence area change is with these differential changes, right? Because in some sense, because we're allowing a version of the differential in x to become a new version of the differential in u, these are both associated to areas. Right, we discovered that from our differential forms section, that's how we construct areas in multidimensional calculus. They're both associated to areas. The x plus 1 versus the 1/2 accounts for our notion of geometric equivalence. That's why we have to make that differential change when we do a u substitution, is all because of this idea of geometric equivalence of a coordinate transformation. So I kind of describe in more detail what we're actually doing as a coordinate transformation, the variable u there, if you want to see it in a different light. But I think you believe me by now that that is a version of a coordinate transformation that we've been using our whole lives. So now we're going to head into kind of doing this as generally as possible in multidimensional cases, because that's what we'll want to do, is just take any multidimensional integral. It might have 17 dimensions in it and perform a very useful coordinate transformation. So let's just analyze what that might have to look like in higher dimensions. So we'll start with a coordinate transformation of a function, right? Because earlier we were coordinate transforming points. We were just taking a Cartesian point and transforming it by plugging it into phi. Well, because a function has a point on the inside and it has a point on the outside, right? It takes in a point and it outputs a point. We're actually allowed to perform 2 different coordinate transformations every time we transform a function. So one of those coordinate transformations is going to happen on the input. So I'll call this the input transformation. And then one of those coordinate transformations is going to happen on the output, and I'll call this one the output transformation. And they're definitely allowed to be 2 different transformations. Right? We could transform Rn as the input, and we could also transform Rm as the output, and those transformations don't necessarily need to agree with one another, but we do need to figure out, if we are going to transform them, how should the function f change? Well, the function f changes if we change both the input and the output as the following. We call it f phi, and then that's another phi. They're both versions of phi, but f of the first phi, comma the second phi, so we keep track of those transformations. Well, it of course inputs the modifies is the new coordinate system for input. And how should f output? Well, it outputs as you're going to take that new input, you apply the inverse transformation of kind of that x coordinate system. So you're going to apply the inverse transformation of that x coordinate system first, and then you're going to apply the regular function, and then you're going to apply the forward transformation of the y coordinate system of the output. So there's the forward transformation that goes backwards. So it's really a 3-step process. And if you took linear algebra, this should look familiar, because in linear algebra, you get something like the transformation matrix, and then the matrix you want to transform, and then you take the inverse transformation matrix. And sometimes this will give you like a diagonalization, for example. And that's really what's happening here, except we're allowing ourselves, because we're in any number of dimensions, we could allow either of those transformation matrices to technically be different functions, not necessarily matrices. But this goes back to very similar ideas to what you've seen in linear algebra, if you've taken linear algebra, that you can take T inverse and then M and then T, and you'll recover this kind of this modified matrix, which is now operating on a different coordinate system, that the matrix works diagonally on that coordinate system, which is really useful in linear algebra. But of course, that's what we're doing today too, where we have this ability to make things a lot more useful by changing coordinates. So I have a remark that says, what is the definition even trying to say? What it's actually trying to say here is just that this function is going to now map the geometric equivalence of this new coordinate to the geometric equivalence of the regular output, wherever f is going to output something, the geometric equivalence in the new coordinate system of the output as well. And so it's just developed to make sure that all of those geometric equivalences agree. And I've got a nice little long remark here to convince you of that. Second remark that immediately follows the first one, which is kind of annoying, but non-Cartesian coordinate systems are almost never vector spaces. So we got really lucky with Cartesian coordinate systems. If we have something like x, y, z, we can actually associate this as the vector x, y, z using an isomorphism that maps a coordinate space to a vector space. That's only true with Cartesian coordinates. So we basically are going to stop using vector notation if we're working in other coordinate systems, because other coordinate systems are not vectors. So what I'm trying to say here is don't use r comma theta for polar, because r comma theta is not a vector, in the sense that if you took a constant and you multiplied r comma theta by it, that's very much not equal to that constant times r comma the constant times theta. So there's not really a vector space hiding behind other coordinate systems. So we're going to stop using that vector notation. It's just something you get to do at this point in calculus, unfortunately. We no longer get to use the elegant vector notation if we're using different coordinates. Let's look at transforming a function into polar coordinates. I know I'm relying pretty heavily on polar coordinates, but they are one of the more useful coordinate systems that we're going to experience. So we did just talk about the definition of transforming a function, and we can transform a function's input into a different coordinate system, or we can transform its output into a different coordinate system. Let's take the function whose first output is x squared plus y squared and whose second output is xy, and let's do every single possible case of either we can transform that into polar, or we can transform that into polar, or we can transform both into polar. And so that's what I have here for 1, 2, and 3. So we're either going to go from a polar coordinate system to a Cartesian coordinate system, we can go from a Cartesian coordinate system to a polar coordinate system, or we can go from a polar coordinate system to a polar coordinate system. And each of those is going to look different in terms of how we would actually transform the function. So in this first case, if we start with my function, which recall was just x squared plus y squared comma xy, what do we do if we want to transform into a function whose inputs are allowed to be polar coordinates, r and theta, but whose outputs I want to associate as the Cartesian outputs that we originally had? Well, following that definition of the transformation of a function, we basically say, hey, if I'm transforming the input into polar, that means I have to keep the polar inverse on the far inside of my function. And if my output I'm keeping as Cartesian, I just use the identity function as my outside function. Well, the identity function is not doing anything, so we're really just like taking f composed with the polar coordinate transform inverse. And of course, that's just defined as f of the inverse transform of r and theta. But we know that the inverse polar transform of r and theta is r cosine theta for x, and it's r sine theta for y. And then we just go ahead and evaluate r cosine theta, r sine theta inside my function f, which gives me r squared cosine squared plus r squared sine squared as the first output. It gives me r cosine theta, r sine theta as my second output. Now, of course, if we want the Pythagorean identity, we can simplify this for us because we have sine squared plus cosine squared. And so we can simplify that term if we would like to as just r squared, and then my second term is r squared cosine theta sine theta. So this, right, this is now a geometrically equivalent function to the one I started with, but it has the ability to take in polar coordinates. That's what we want to think about this function. It takes in polar coordinates. Now, the outputs are still going to be interpreted as Cartesian, but it has the ability to take in polar coordinates. We can do the reverse, which is to allow ourselves to keep the ability to take in Cartesian coordinates, but let's say maybe I want to output into the polar coordinate system. And of course, all that happens here with this weird inverse function stuff is that we're going to kind of reverse the order of what we had before. We're going to keep the Cartesian coordinate system as the input side. We're going to give ourselves the polar coordinate system as the output side. And so when I put the identity function inverse, it's just the identity function, so it doesn't do anything to x and y. But then I'm going to apply the function f to x and y, which if you remember what that looks like, it looks like x squared plus y squared is the first output, and then xy is the second output. And then that is currently written in Cartesian coordinates. I would like to transform them to polar, which is why I'm applying phi to the outside of those. And of course, phi in polar coordinates is going to take the x entry, which is not just x here, but the x entry, and it's going to square the x entry, and it's going to square the y entry, and it's going to put a square root around those to recover a radius. And then it's also going to take the y entry into a tan 2, and it's going to take the x entry into a tan 2. And so now this output is the polar coordinate output of my function whose inputs are allowed to be Cartesian coordinates. But it's geometrically equivalent to the original function that was just mapping Cartesian to Cartesian. And then finally, when we want to have the ability to input a polar coordinate and then also output a polar coordinate. And so what we see on this side is both sides, right? Both sides of this composition are going to include the coordinate transformation. Of course, the inside has that inverse that it always picks up. Then when we apply the inverse on r and theta, of course, we send r and theta to their x output and then their y output. So we're back in Cartesian coordinates. This is what allows us to actually act the function f on them, because f only acts on Cartesian coordinates. And so it takes the x input and it squares the x input, it adds it to the y input squared. And then we also have, this is x times y in the second case. There's the x input and the y input in the second case. Then finally, this current point is kind of interpreted as a Cartesian point, but that's not the point we want it to be interpreted as. So we would rather it be back in polar. And so when we put it back in polar, we're going to act one more round of phi on it. And so phi will take the x input and the y input, and it's going to square both of them. It's going to put a square root around that for r, right? For kind of the output radius. And so this is what you end up getting for that output radius. And then you also have that a tan 2 function on y, comma, x. So if you simplify the a tan 2 a little bit, it turns out you can actually cancel these r squareds if you want to with an a tan 2. And so that's why I just have a 1 right there. But this would then be the output of the function in polar coordinates. So now you can see the function from polar to polar takes in r and theta, and it outputs, well, a function of r and a function of theta as a kind of a coordinate that is like the new radius, and the new angle. So those are all of the possible ways we can transform functions, just depending on what we want. Sometimes we may want to have the ability to input in one coordinate system and output in another coordinate system. That's kind of how you do it. Most important for integration, however, is transforming the differential. This is the most important part of integration against coordinate transformations, is how should we transform the differential. So it turns out that the differential of our Cartesian variables, the differential of x, these are our Cartesian variables, our Cartesian point, the differential of that transforms into a new coordinate system phi as, well, you take the differential of phi, this is really the total derivative of phi inverse, okay, so you take that total derivative of phi inverse, evaluated on the new coordinate system point, and then that multiplies, this is actually a matrix, right, so it's a matrix multiplication against the vector d in the new coordinate system. It's the differential in the new coordinate system. So we pick up this matrix of d phi inverse. That's really what we want to keep in mind, is if we transform a variable, transform the variable in an integral, the price we pay is the matrix of the inverse of the coordinate transformation. So the price we pay is going to be the matrix of, which is the differential of the inverse coordinate transformation. Now this has a very important role, specifically when we deal with the volume form, right? Because the volume form is the wedge product of each entry in dx, in the differential of our variable. You take each entry in the differential, you take the wedge product of all of them. That's what this volume form is that we've been working with the whole time. Well, how is that going to play when we have this idea of d phi inverse, which is multiplying kind of the new coordinate system? If I take the wedge product of all of the terms of the output here, what ends up happening is I just pick up the determinant of that matrix. Right, you're going to pick up the determinant of that matrix from the wedge product. Remember, there's this isomorphism between determinants and wedge products of vectors because they both represent the volume of parallelepipeds, or however many dimensions we're in. There's that isomorphism between determinants of matrices and wedge products. And so you find out that when you transform a volume form, the price we have to pay is the determinant of the differential of the inverse transform. And that's what this corollary is saying, and it's probably the most important thing you can take out from today. So I'm just going to write that down. Most important takeaway from today is when you transform coordinates, the volume form, which is kind of the most important form in multidimensional integration, the volume form gets multiplied by the determinant of the derivative of the inverse transform. We're going to keep that in mind for the rest of today, and actually for the rest of this section when we handle the next video as well. So you multiply the volume form by the determinant of the derivative of the inverse transform. So let's see this in action with polar coordinates. Here we have something called an annulus. Annulus comes from the Latin word for ring, and hopefully looking at the picture of the annulus, you can figure out why. It comes from the Latin word for ring. In other words, it's a circle with a smaller circle cut out from the center. And in multidimensional notation, if we just talk about it as a domain, we're talking about x squared plus y squared being bounded above by 4 and bounded below by 1. And that's because this is a radius of 1 and it's a radius of 2, 2 being the square root of 4. So we have this annulus here. And let's go ahead and see if we can find the area of the annulus. Now, it's not going to be too hard to do the area of the annulus using geometry, right? We just have the area of the inside circle, which is going to be pi r squared. Well, if r is 1, that's just going to be pi times 1. And the area of the outside circle, if that's a radius of 2, is going to be pi r squared. So we're going to have 2 pi minus 1 pi. We're going to get an area of 3 pi is what we expect to get. But let's see if we can get the area of the annulus using multidimensional integration. Can we agree with 3 pi using multidimensional integration on this domain? Well, big downside, if we try to write the domain as a normal domain in Cartesian coordinates, it requires 4 distinct subregions, or I'll call them subdomains. It requires 4 distinct subdomains. And the reason is because of how many times I fail the vertical line test, or even the horizontal line test. Like, it doesn't matter if I tried to do bounds on x as constants and then the variable y bounded as functions of x, or y bounded with constants and then the variable x bounded as functions of y. Notice, sure, you pass the vertical line test for a little while, but eventually you stop passing the vertical line test, and so you have to write this region as its own domain. And then you start passing the vertical line test again, so you get yet another domain, and you have to account for this bottom piece that you've missed as its own domain as well. And so we have 4 different subdomains that we have to take care of here, between -2 and -1, and then y is bounded on the left-hand side below by negative root 4 minus x squared and above by root 4 minus x squared. And then we have this top half, which is where x is between -1 and 1, and then y is bounded below by the inside radius, which is root 1 minus x squared, and then above by the outside radius, root 4 minus x squared. Then we just continue. We have our 4 distinct regions that we have to integrate over. Turns out when you integrate each of these, you require a trig substitution for each. So you're doing like 4 different trig substitutions just to get this problem solved. And the area of the first place is 4 pi over 3 minus root 3. The area of the second is pi over 6 plus root 3. The area of the third is pi over 6 plus root 3. And the area of the fourth is 4 pi over 3 minus root 3. You add all those together, and lo and behold, you get the right answer. It's just really not fun. So hopefully there's a better way of integrating this with multi-dimensional calculus. And of course there's a better way, which is to perform a coordinate transformation into polar coordinates. So let's just go up really quick and think about this shape in terms of the polar coordinate system. So I'm going to place the polar coordinate system on here, and we can see if we can come up with a way to describe the region in polar coordinates. How far out do I have to go to get to the first annulus? Well, that's a radius equal to 1. And then what is theta? Well, theta goes all the way from, you can call it 0 to 2 pi, or you can say negative pi to pi. So theta is in, I'll say negative pi to pi for the inside bound, and then my outside bound, r goes all the way out to r equals 2, and theta, once again, goes all the way around the circle. So theta is very much unrestricted here. So theta is going to be in negative pi to pi again. And so really, in polar coordinates, you would expect that all we need is the interval between 1 and 2 for r. Now let's say that you didn't know how to plot one of these regions, and you just want to arrive at the same value using your coordinate transformation directly. Well, you can certainly do that just by working with omega algebraically. So this is omega as we originally defined it. Like, imagine you don't even know that it is a annulus. You could probably be ready to use polar coordinates on it anyway by recognizing an x squared plus y squared. Anytime you have like 2 things squared, you're thinking about a circle of some sort, right? So x squared plus y squared. So you would want to use polar coordinates anyway, just by recognizing that x squared plus y squared there. And then how do you transform the region algebraically using polar coordinates? Well, you know that x is equal to r cosine theta, and you know that y is equal to r sine theta. So you just replace x right here with r cosine theta, and you replace y here with r sine theta, and then you simplify. And of course, the Pythagorean identity tells you can simplify those terms just into r squared, and then we see that really omega is just this sort of interval in r squared, or you take a square root of every side, and you find out that you have the interval between 1 and 2 for r. Now, you may be wondering, when you take a square root, why didn't we also get, right, you should have the interval -2 is less than r is less than -1. You do also get this interval, but recall that in the polar coordinate system, r is only allowed to be positive anyway, so that kind of r is between -2 and -1. Extra little region that you pick up just doesn't make any sense in polar coordinates. And so you can omit that and you just get 1 is less than r is less than 2. That's purely algebraically. And so it's really nice that you can just transform the region omega algebraically using polar coordinates, and you immediately recover this very well-behaved normal domain just in the variable r. And of course, because there's nothing that restricts theta on the right-hand side, we know that theta is just going to take every value that it can, -pi to pi. So that's how we could at least transform the region. Now we may want to find the volume of the region, right? And the volume of a region is always just going to be the integral of the volume form over that region. So we have the integral of 1 dv, but that's in Cartesian coordinates. Now we're going to have the integral of the volume form in r comma theta. And the big question is, should this still be 1? Because we just talked about the most important part of today, which is that we need to multiply the volume form by the determinant of the differential or the derivative, whatever you want to call it, of phi inverse, of the inverse transformation. So we got to figure out what the inverse transformation is, compute its derivative, and then compute the determinant of that, and that's what we're going to include on the inside of our volume integral. Well, we know that phi inverse, right, phi inverse of r and theta is just this x value, which is r cosine theta, and the y value, which is r sine theta. It's not too hard to take the total derivative of that, right? I know how to take the total derivative of something with two variables. There's an r here, there's a theta here. I'm just going to go partial r on this point. Thankfully, it's a Cartesian point. I'm going to do partial theta on that point. It's a Cartesian point. So you can represent them as vectors because they are Cartesian points now. And so you represent them as vectors, you take partial r, and of course what do you get? You just get cosine and you just get sine. You take partial theta, you're going to get negative r sine and you're going to get r cosine. So that's the total derivative of phi inverse as a matrix, and now we're going to take its determinant. So when we take the determinant of this matrix, really not too hard to take a determinant of a 2 by 2 matrix, AD, right there, r cosine, minus BC, negative r sine, we're going to get r cosine squared plus r sine squared against the volume form, which is going to give me r dv. So now when I'm integrating over omega, I can either do the Cartesian version in x and y with a 1, or I can do the polar version where I just discovered I need to pay the price of the radius r. And so that's going to be my integral to find the area of this annulus. And I know that my domain just said, hey, r was between 1 and 2, theta is between 0 and 2 pi, or negative pi and pi. I'm really not too worried about those values of theta because everything is equivalent. And then you're just going to integrate in the variable r, which gives me r squared over 2. And then r is, of course, between 1 and 2. So we get 2 squared over 2 minus 1 squared over 2. That gives me 3/2. And then I integrate theta from 0 to 2 pi. That's giving me 3 pi. So a much easier integral. I did not have to split the domain into 4 different pieces. And I just made sure to take the determinant of the derivative of the inverse transformation. That's what gave me this r right here. Okay, and then we're almost done, but I'm going to give you one more example for coordinate transformations, making our life easier. And one more example of integration here. It's kind of a non-trivial coordinate transformation, just one that we're going to kind of surmise out of nowhere. Not completely out of nowhere, and we'll see where it comes from. But suppose I have this integral here that I'd like to integrate over omega. It's an integral of 2 variables. And our function is x minus y times e to the x squared minus y squared. Let's say that omega is where 1 is less than x plus y, which is less than 3, and negative 1 is less than x squared minus y squared is less than 1. And the region is shown below here, right? There's that region for omega. Not really the prettiest thing, definitely not written as a normal domain for now. So big question, Q, can I force a normal domain with a coordinate transformation? And the answer is yes, I definitely can, because what do I see here? I see x plus y, and I see x squared minus y squared, but of course x squared minus y squared is really just the difference of squares, so that's going to be x plus y and x minus y. What do you know? This x plus y thing is showing up a lot. Maybe let's give that the name of a new variable, and then we also have an x minus y here, so let's maybe transform into this idea of an x plus y and an x minus y as our new variables. And so that's what I have here as phi. Let's do a coordinate transformation where phi maps x comma y to the variables x minus y and x plus y. So I kind of felt like it should be pretty natural out of both of those terms showing up quite a bit in my domain, even though my domain wasn't a normal domain. Notice if I actually perform that sort of replacement as the output of phi, whatever I call this variable is now bounded by constants, and then you kind of have two variables multiplied together, which are also going to be bounded by constants. So your life would get pretty easy if you can pull off this coordinate transformation. But what do we need to verify about this? We need to verify two things. First, that it's invertible, and second, that it's continuously differentiable. Of course, the second one goes pretty quick. Those are just linear functions. Linear functions are definitely continuously differentiable. We do need to find the inverse of phi, however. So this is where kind of that inverse function theorem can be useful. We're a little lucky in this case. Everything's linear, so we can use linear algebra to find the inverse function. All we're going to do is say, hey, if I need to find an inverse function, I'm giving myself a new variable, z and w, by the way. Let's say if I want to find the inverse function, I'm just solving this system of equations for the variables x and y. And of course, that system of equations is just the matrix 1, -1, 1, 1 acting on x, y. And so to find and solve for the variables x, y, I'm just going to compute the inverse, 1, -1, 1, 1, inverse on z and w. And we have linear algebra formulas that tell us how to do that. Turns out when you do the inverse on z and w, you get z plus w over 2 is a representation of x, and negative z plus w over 2 is a representation for y. And so that's going to be your inverse function. Right? The inverse function takes in z and w, and it gives you z plus w over 2 as your x coordinate, gives you negative z plus w over 2 as your y coordinate. That's going to be very useful because now we can find the volume form, right? The volume form, or the volume differential, will change by what I've been saying the whole time. The most important takeaway is you need to multiply by the determinant of the derivative of the inverse transformation, the inverse. And so if I take the derivative of that inverse transform that I just came up with, this one right here, take the derivative of this inverse transformation, what do I get? Well, you take partial z, that's giving you 1/2, 1/2. You take partial w, that gives you negative 1/2, 1/2. Then we need the determinant of this matrix. That's pretty easy to compute. The determinant will just be 1/2. So that's the price I'm paying to change my coordinate system. It's just a multiplication by 1/2. Now let's go ahead and change the domain with respect to my new coordinates. So this domain omega, remember I had an x plus y and an x squared minus y squared as my two special terms here. I'm just going to take the value of x, which comes from the inverse of phi. I replace x with z plus w over 2. I replace x with z plus w over 2. I replace y with negative z plus w over 2. Both cases that y shows up. Then when I simplify those, the left-hand inequality just becomes 1 is less than w is less than 3. So there you go, that's already kind of in a normal domain. My second piece, negative 1 is less than z, w is less than 1. It's not quite a normal domain, but notice that because w is already bounded by constants, I'm just going to divide both sides by w and get negative 1 over w, positive 1 over w is the bounds on z. Okay, so now that we've established our normal domain, we can actually go ahead and compute the integral. Let's recall what the integral said. It said integrate over omega x minus y e to the x squared minus y squared against the volume form of x and y. Of course, we're going to replace this volume form with 1/2 times the volume form of z and w. That's what I have here. And then we're going to replace x with its version of z and w, which is z plus w over 2. And there's two cases of x here, right? Here's the other one, z plus w over 2. And then we have y in its version of z and w, which we'll replace with negative z plus w over 2, and another case of negative z plus w over 2. When we simplify all of those things out, we actually just get z times e to the zw, and then that 1/2 from our volume form just comes along for the ride. And of course, we have our normal domain up here. W is between 1 and 3, and z is between negative 1 over w and 1 over w. So I'm just going to set up my iterated integral, w between 1 and 3, z between negative 1 over w and 1 over w, and I just go ahead and integrate in the variable z first. Thankfully, I have a little integration by parts that I can use in the variable for z. I'm going to get z over w minus 1 over w squared times e to the zw. I'm going to plug in my z's. Lots of things cancel, which is pretty nice from this. We end up just with e to the negative 1 and 1 over w squared, which is what I'm integrating from 1 to 3. And when I take the antiderivative of 1 over w squared using the power rule, negative 1 over w, and evaluate on the bounds, I'm just getting 2/3 e to the negative 1. So really, very hard problem if you don't perform the coordinate transformation. But when you do, still maybe a little bit hard, but nothing insane to actually integrate. And we're going to stop there. It's already been a long one. We're going to head over to spherical and cylindrical coordinates in the next section, kind of the two most useful coordinate systems in 3 dimensions. I'll see you then. Hope you're looking forward to it. Bye.